So chemical quantities and reactions. So we now know the elements, we know how to write compounds, and now we are going to look at chemical reactions, actual chemical reactions, okay? And not only that, we'll also be, calculating. Okay, let me see if I'm recording. Yeah, so we'll also be calculating how much reactant give how much product. Okay, so there's some math involved here. Okay, and the math is simple math, though. It's like our kitchen recipes. Okay, so if you are trying to make some food, you have a recipe, how much should you start with, how much you'll get, this kind of stuff. But we'll be using conversion factor that we learn in uh, in the measurement chapter. Okay, so same idea. So the first thing that we are going to learn here is the concept of moles. Okay, mole is like our chemist dozen. Okay, the way to count is a pure number. Now it's a big number. Okay, it's just like dozen or millions, um, and the mole is the you know is basically a pure number to count. Okay. Now, we use this big number to count atoms and molecules because they're so small. We really do not use it to count larger objects, okay? So it's only for atoms and molecules, maybe electrons. Not maybe, we do count electrons in terms of moles, but it's a pure number, and the number is 6.02 10 to the power 23. Okay, so you have to memorize this number. Now, how we came to this number? Why kind of odd number here? That we'll learn later. So it has a historical importance. Um, so it is a pure number and is also called Avogadros number. So it has several names. It is called the mole. It is called Avogadros number. Okay, um, so either is fine. Uh, now, the standard definition of mole or Avogadros number is that if you take 12 grams, which is the gram molecular weight of carbon, okay, exactly 12 grams of carbon-12 isotope, the number of atoms present is equal to Avogadros number. So the atomic weight of carbon-12 isotope will be exactly 12, right? And if you take 12 grams of that isotope, and if you have means of counting the atoms, the number of atoms you'll get is called Avogadros number. And that is true for all elements that you see here are molecules. So if I take 1 mole of aluminum, that is equal to this many atoms of aluminum. If I take 1 mole of sulfur, that means this many atoms of sulfur. 6.02 10 to the power 23. If I take 1 mole of water, that will be this many molecules of water. Now, so this 1 mole equal to 6.02 10 to the power 23 can be used as a conversion factor. Okay, so you can from any relationship you can get 2 conversion factor. So we can get this 2 conversion factor from this simple relationship. Okay. Now, what we can do with that, we can count, right? So if you are given 4 moles of sulfur, I can tell how many atoms of sulfur are there. Okay. So 4.00 mole of sulfur. So mole S is the unit. So you have to put a tag with the mole. Okay. Otherwise, you might have several moles or different kind of moles of different atoms and elements, the same problem. So you must tag it. Okay, so mole S is the unit. So 4 mole S is equal to 2.41 10 to the power 24 atoms of sulfur, or more or less and more or less would cancel out. and our answer should come out in atoms of sulfur. Next is carbon dioxide, which is a molecule, okay, compound, and we want to convert this many number of molecules to moles, so just the reverse. So in that case, the molecule of carbon dioxide, which is the unit, okay, cancels out, and you get your answer in mole of carbon dioxide. So here's a small guide to calculating atoms and molecules. So state the given and needed quantities. So that is where you want to go, okay, where you are starting. Write the plan, okay, and convert the mole to atoms. And here you are using Avogadros number as the conversion factor, okay. So if you look at the next problem, that's an example, okay, similar example. How many molecules are present in 1.75 moles of carbon dioxide? So your given is 1.75 moles of carbon dioxide, and needed is this many molecules of carbon dioxide. Okay, how many molecules? So that's the question mark. Okay, now if you look carefully, this is the given quantity, 1.75 moles of carbon dioxide, and we want to go to molecules. So your moles of carbon dioxide should cancel out. So that's the idea here. So your conversion factor is 1 mole carbon dioxide is this many molecules of carbon dioxide. So you have two conversion factors. They use the one where the mole cancels out. Okay. And your answer is 1.05, 10 to the power 24 molecules of carbon dioxide. So basically you are doing the similar thing that we learned in the measurement chapter, use of conversion factor. And we are just going to use that for this chapter. But this is for counting molecules. That's the difference. So there we are doing measurement. Okay, we can also count atoms. And so here we counted molecules of carbon dioxide. We can also count the atoms within a molecule if you know the formula. So if you look at formula, so formula can also be a conversion factor. Okay, if you look at this formula C9H8O4, that's aspirin. What it tells you that if you take one molecule of aspirin, it will have 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. So if you take 1 mole of 1 mole of aspirin, okay, then it will contain 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So basically multiplied everything by 1 mole. And so these are all the conversion factors that you can generate, okay, from this simple relationship. So you can basically count the carbon atom or hydrogen or oxygen. Now the idea is your previous unit should cancel out, okay, and the given unit remains. So here you have a simple question like propyl acetate, that's a compound, okay, is C5H11O2. How many moles of carbon are present in 1.5 moles of propyl acetate? So you are given 1.5 moles of propyl acetate, and you want to figure out how many carbon atoms are there. Okay, so that means your propyl acetate, moles of propyl acetate should cancel out, and moles of carbon should remain. So if you look at the relationship between propyl acetate and carbon, so you see this pink block here. So this is the relationship, and we can get two conversion factor. We are going to choose the one for which the moles of propyl acetate is cancelling out and moles of carbon remains. Now 5 is the exact number, okay? So there is no, it's a count, there's no error. So our significant figure will depend on 1.50. So that's 3 significant figure. So our answer must be in 3 significant figure. And so the correct answer is 7.50 moles of carbon. So there's another conversion factor that, so we use the Avogadros number as conversion factor We use the formula as conversion factor. The third one that we are going to use is molar mass. So what is molar mass? So molar mass is defined as the quantity in grams that equals the atomic mass of an element or molecule of a compound. Okay. Uh, so that means you can say that it equals the atomic mass of the element. That means if we express the atomic weight in grams or the molecular weight in grams, like if you are taking, let's say, sodium, the sodium is 23 atomic mass. So if you take 23 grams of sodium, that is called the molar mass of sodium. And the molecular weight of water is 18. So if you take 18 grams of sodium water, that will be 1 mole of water, or the molar mass of water. Okay, so so we are counting this many atoms of the element when you are actually weighing out the element in molar mass. Okay, so if I take 23 grams of sodium, that means it will contain 1 mole or 1 Avogadros number of atoms. Okay. So if you look at carbon, carbon has an atomic mass of 12.01. That's the average atomic mass. So 1 mole of carbon atom, if I take 1 mole of carbon atom, it will have a mass of 12.01 grams. Okay. So for molecular weight, you just add up the atoms, like water is H2O. So if you add up the atomic weights of hydrogen and oxygen, you'll get the molar mass of water. Okay. And in that case, hydrogen is 1. So 2 hydrogen is 2 and oxygen is 16, total 18. So if I take 18 grams of water, that will contain Avogadros number of water molecules. So very simple idea. So here we have a question. A piece of jewelry requires this many mole of silver. How many grams of silver were there? So you want to go from moles to grams. So in order to go to grams, you need the molar mass. Okay, so the molar mass of silver, if you look in the periodic table, the silver has an atomic weight of 107.9. So 1 mole of silver is equal to 107.9 grams of silver. And we can use that as a conversion factor. So this is the molar mass. Okay, we can use that as a conversion factor. And we have to use it such that in this case, you are given mole of silver. So mole of silver should cancel out and gram silver should remain. So 0.75 mole of silver is equal to 80.9 grams of silver. Okay, so in this chapter, we are using 3 conversion factors, only 3. Avogadros number, formula, and molar mass. So here the mole and mole cancels out, you are left with grams. Chemical reaction. So we are done with the quantities. Okay. Now writing chemical equation. So when you are writing a chemical equation, you have the reactants on the left-hand side and you have the product. Okay. So now that we know formulas, we can write formulas for the reactant and the product. And here the several reactant, carbon and oxygen, 2 reactant, giving 1 product, carbon dioxide. Okay. Now, when there are 2 or more formulas, we add a plus sign in between, and then there's an arrow, and we can, add other things like delta. Delta means heat. Okay, you can add physical states in parentheses, like S and G. S means solid, G means gas. So we kind of add, other informations into the equations gradually. Now, if you look at this equation here, you have 1 carbon, this black ball is carbon. Okay. Uh, and we have one carbon on the right, one carbon on the left. We have two oxygen on the left, two oxygen on the right. So this is balanced. That means uh, the law of conservation of mass says that atom is neither created nor destroyed. So when you perform a chemical reaction, the number of atoms of the element should not change. So we have same number of atoms in both sides. So that's good. But it may not be so all the time. Okay. Like if you look at this example here, CH4 plus oxygen. Okay. So we have two reactants, but and two products, carbon dioxide and water. Now, if you count the number of carbon atom, you have one carbon atom and one carbon atom, both on the left and right. If you count the number of hydrogen, you have four hydrogen on the left, but you have two hydrogens on the right. For oxygen, you have two oxygens on the left and three on the right. So these are unbalanced. So we cannot, so it is not conforming to the law of conservation of mass. The masses are different, and that cannot be. And so we need to balance the equation. Okay. So balancing equation is basically, we are balancing it to keep to the law of conservation of in a matter. Okay, that all atoms are conserved during chemical reactions. So there should not be any gain or loss. Um, so uh, every chemical reactions must be written as balanced, which shows the same number of atoms on both sides of the reactant and the product. Okay. And so when you balance it, you can use whole numbers called coefficients in front of formulas. That means I can use whole number in front of this, which means that if I put a 2 in front of water, okay, that means two molecules of water. So when I'm saying water is formed, I never said how many molecules, right? They need not be equal, carbon dioxide and water. Who said that? Okay. So we can change the number of water or carbon dioxide such that we eventually balance the number of atoms on both sides. Okay. And this is called balancing of uh, in a chemical equation. And very, very important thing. Now, there is no chemistry there. Once you write the formula, it's like trial and error, and you are as good as I am. And sometimes my students are better. They do it faster than I do. It's like puzzle solving. Okay, you look at it, and there are some certain, procedures that you can follow. Otherwise, once you get good at it, you look at it, and my students put number there immediately. Okay, before I do it. So again, no chemistry. So how can you balance it? Uh, so if you look at this formula or this equation here, the carbon is balanced, so we don't need to bother about carbon here. So this carbon is balanced. Okay. Now, if you look at hydrogen, if I put a 2 in front of water, because there are four hydrogens, like, so there are total four hydrogen. So if I, instead of one molecule of water, if I take two molecules of water, then I'll have four hydrogens. So I put a 2. And you go back and forth. Okay. So now you balance the hydrogen. Now, once you balance the hydrogen, your number of oxygen basically changed on the right-hand side. Now, because there's a 2 water, you have 2 oxygen from carbon dioxide and 2 from water now. So total 4 oxygen are there on the right-hand side. So in order to make 4, you put a 2 in front of oxygen, because oxygen is diatomic, O2, total 4 atoms. Okay, 4 oxygen. So you go back and forth. Okay. So now everything is balanced. So this is how you balance chemical reactions. Now you can, so there are certain rules you can follow. Okay. Uh, and the rules are basically that you always start balancing that element that is occurring only on one compound on the reactant side and one compound on the product side, because that makes it easier. It's just common sense thing. Okay, if it is in several compounds, I cannot balance it at once. Okay, so you are trying with the easiest one to balance. Okay, so the easiest one here is the one that occurs on only one compound on the reactant side, one compound on the product side. So that's why I started with hydrogen, because if I fix the water, I'm done. Okay, so that's the first criteria. And the second criteria is if there's an element like oxygen, you balance it at the end. Because the element has only one kind of atom, it's easy to balance it because you are just changing one of the element only, rather than a compound which can have several different kinds of atoms or of different elements. Uh, so, and these are common sense thing. Again, no chemistry. So people who solve this, figured out that that's the easiest way of doing it. Okay, of approaching this problem. Now you can use fractions. Mathematically, they are correct. Okay, like you have Al plus Cl2 to give AlCl3. So Al is balanced. I need 3 chlorine. How can I get 3 chlorine? Okay, each chlorine is diatomic. That means each chlorine contains 2 atoms. So if I take 1.5 of that, right? That is 3 atoms. Because each is 2. If I take 1.5, that means 3 by 2. So when I'm writing 3 by 2, see what is happening is I am using the fraction such that this 2 and this 2 cancels out. And I'm left with 3. So I'll get 3 atoms of chlorine. Okay. Now this is balanced, but the only caveat is that even though this is balanced mathematically, but molecules cannot be fraction. So what do I do? So I have to get rid of the fraction. In order to do that, you multiply this whole equation by 2.
Oh.
So if you multiply by 2, then you get 2Al, and 3 by 2 chlorine now becomes 3 chlorine, and you have 2AlCl3. Now if you check the number of atoms on both sides, they're equal. So these are simple techniques. Again, common sense technique developed, you know, uh, is like more like puzzle solving. Okay, so if you want to solve this puzzle, you have to start from the element that only occurs in one compound. Okay, on the reactant side, one compound on the product side. Balance the element at the end, like we did for the one above.
Mm.
Okay, of methane. This this oxygen was balanced at the end. Okay, uh, and if you use fraction like this, then you after you get mathematically correct equation, you have to get rid of the fraction. Okay, now this is a polyatomic ion, and the polyatomic ion is appearing on both sides same. In that case, take the polyatomic ion as one single entity. Don't look at it as phosphorus and 4 oxygen. Look at it as one single entity. Okay, that means uh, I have one phosphate on this side. Okay, on the reactant side, and I'll take it as 3 phosphate or 2 phosphate. All right. So the next type of reactions that we'll look at are the redox reactions. Now, so far, redox reactions involve transfer of electrons. So there's actually electron transfer from one substance to another. Okay. Now, if one substance loses electron, then another substance must gain the electron. So there's always a acceptor and a donor of electron in this type of reactions. So you have to identify who is losing the electron and who is gaining the electron. Electrons, remember, electrons are negatively charged. Okay, so often forgotten. Um, now you have to know this definition. Oxidation. So if something is getting oxidized, another thing is getting reduced. So oxidation means loss of electron, and reduction means gain of electron. Okay, now how do I remember this? Now, one easy way of remembering it is you use the acronym. Okay, we say oil rig, OILRIG. So oil rig, if you look at O, that's oxidation for loss of electron, and reduction for gain of electron. Okay, so we are just taking the first letter. So now, if you look at this reaction, copper plus oxygen to give copper oxide. So you have to basically see what is happening. So copper was 0. 0 means is elemental state, no charge. Okay, oxygen is the elemental state is 0. Okay, no charge. Okay, now if you look at this compound CO, oxygen is 2 minus and copper is 2 plus. So when the compound is formed, you can see that this copper becomes copper 2 plus and oxygen becomes O2 minus. How can that be? So copper 0 becomes copper 2 plus by losing electron. Okay, and this is oxidation because copper is losing electron. Okay, oxidation. And if you look at oxygen, oxygen is gaining the electron. So oxygen is getting reduced. So if you see O2 2 minus is becoming 2O2 minus if you balance it. Okay, so that means so copper is losing 2 electron, oxygen is getting 4 electron. So you need actually 2 copper to do the job, right? So number of electron needs to be same. Okay, and because the number of electron needs to be same, that can also be a basis for balancing equations. So you write the oxidation reaction. Okay, once you see a reaction like this, okay, you figure out who is getting oxidized. So I can see that copper is becoming copper 2 plus. Okay, so this is oxidation and this is reduction. So after identifying who is getting oxidized and who is getting reduced, okay, now you have to make the number of electrons the same. If you try to make the number of electrons same, okay, which is 4 electrons, right? So so this reaction, if I multiply by 2, I'll get 4 electrons and then add them together. Okay, add them, and that is your final balanced reaction. Okay. So that is exactly what we did here. Okay, so we multiplied in order to make 4 electrons. Okay, we multiplied the first equation by 2. Okay, so the overall equation for the formation involves an oxidation reduction that occurs simultaneously. The number of electron lost must be equal to the number of electron gained. So therefore, we multiply the oxidation reaction by 2. And if you multiply by 2, then 4 electrons cancel out. And if you add them up, this becomes a final balanced equation. So electron transfer, we can use electron transfer to balance, chemical equations. There's another method of balancing. Now, this is another example. Zinc plus copper sulfate to give zinc sulfate plus copper. Now, if you rewrite the equation, Okay, you have zinc 0, okay, copper 2 plus, copper sulfate is copper 2 plus, okay, aqueous, and sulfate, okay, SO4 2 minus, to give zinc 2 plus, okay, and sulfate 2 minus. Now sulfate is common, right? So you can basically cancel out the sulfates. So you can basically cancel out the sulfate is common. So I can basically cancel out the sulfate. So what is happening is zinc 0 is becoming zinc 2 plus. So I can see that here. And copper 2 plus is becoming copper 0. So if you write the oxidation, so these are oxidation reaction. Okay. So here you can see zinc 0 is becoming zinc 2 plus. Now you have to balance the charge. So this 0 and this 2 plus, that means I can balance the charge by putting 2 electrons on the right hand side. And you can see the charge is 0 on both sides. Okay, because electrons are negatively charged. Okay. Similarly, I can write the reduction reaction here. Okay. And copper 2 plus plus 2 electron to become copper. Now from here, you will be asked 4 questions. Only 4. Okay. So what is getting reduced? What is oxidized? Okay, what is reduced? What is oxidized?
Zinc.
What is oxidized? Okay. And what is reduced? So here, what is oxidized? Zinc metal is getting oxidized to zinc 2 plus. So simple answer, okay? What is reduced? So oxygen is getting reduced. And it is forming, copper 2 plus is getting reduced. Okay, in this case. What is reduced? And the another term is the agent, the oxidizing agent. So who is the oxidizing agent? Agent is the one that is doing it. So if zinc is getting oxidized, it is done by copper 2 plus. So 3 is oxidizing agent. Okay. Oxidizing agent. Who is the oxidizing agent? So here, so what is getting oxidized? In this case, the correct answer is zinc. Okay. And what is getting reduced? The correct answer is copper 2 plus. Copper 2 plus is getting reduced. Okay. And who is the agent? Oxidizing agent. If zinc is getting oxidized, it is done by copper 2 plus. The other guy, right? So is the agent making zinc to convert, and reducing agent. So who is the reducing agent here? So you see copper 2 plus is getting reduced. So the agent is zinc.
Yeah.
So the agent is zinc. So these are the 4 in a common type of question you get. Any question up to this point? So these slides are basically the summary of the chapter. I basically copied it from the book. Okay, photocopied and rewrote myself. This is not exactly the publisher side. So you have all, most of the materials here. Kind of, you can say, the gist of the chapter. So the characteristic of oxidation reduction is always involves loss of electron. Okay, and when there is a loss of electron, oftentimes there's an addition of oxygen or loss of hydrogen, and gain of electron is accompanied by loss of oxygen, gain of hydrogen. Now, this definition is helpful in biochemistry. Okay, so we often see addition of oxygen or loss of hydrogen. Okay, in biochemical reactions. So addition of oxygen, as the name suggests, oxidation. Addition of oxygen is oxidation. So loss of hydrogen, the opposite, is also oxidation. Similarly, loss of oxygen is reduction and gain of hydrogen is reduction. So we use that in biochemistry, okay, in biological reactions mainly. And there are, very common important reactions like NADH, FAD. Okay, you can see this biological molecule, reacting with this coenzyme FAD to give FADH2. So there's the addition of hydrogen. So this is a reduction reaction. So the FAD is getting reduced. Okay, and the biological molecule is getting oxidized. Okay, another good example is NAD, NADH. So these are, molecules will come across in your biological classes. Okay, and this is what is happening. Now, the cell, basically utilizes NAD. So I was talking about mitochondria being the powerhouse. So when you consume glucose, there's a glycolysis step that breaks down the glucose to pyruvate. Okay, and eventually that pyruvate enters the TCA cycle, the tricarboxylic acid cycle, also called the Krebs cycle. And then this 3-carbon molecule basically breaks down to carbon dioxide. Now, as it is breaking down to carbon dioxide, it produces NADH, which is basically a electron-rich molecule. Okay, high energy electron-rich molecule. Now, this NADH then enters the oxidative phosphorylation. Okay, so these are enzymes that are lined up in the inner wall of mitochondria. Okay, and mitochondria is double membrane. Remember, okay. And so what happens as the electron gradually steps down from NADH and eventually get accepted by oxygen in step by step. So that's why we need oxygen. Okay. So oxygen is the ultimate electron acceptor. But as it is stepping down, so if you think of the mitochondria, so it's kind of, double walled like this. So this is the I did the opposite. So you can think of the mitochondria as it has the outer thing, and so actually there are something like this. Okay, so that it gets a large surface area here. So there's double wall, and these enzymes are basically sitting here in the inner mitochondrial wall. So the electron basically moves from one enzyme to other. Okay. So as it's stepping down, okay, it pumps out H plus ion. H plus ion. So this inner membrane space, pumps out this is get filled with H plus. The H plus is acid. That means it becomes highly acidic. Okay, so there's a gradient created then. You have a lot of H plus here and not much in the inside. Okay, so there's this enzyme ATP synthase. Okay, it's a huge enzyme sitting here. So what happens? This proton basically passes through this enzyme, okay, and turning it like a rotor. So it basically, it's a multi-subunit, huge enzyme. Uh, it turns it like a rotor. And what happens is ADP is diphosphate, gets
Mm.
converted, reacts with
That was.
a phosphate to give ATP. So a phosphate bond is getting formed. So what you are seeing here is the energy of the electron is getting converted to the energy of the acid gradient. And then finally, ATP synthesis is utilizing that acid gradient to produce, chemical bond, which is our energy coin.
Mm-hmm.
We utilize ATP. We cannot use it in any other form. The energy, when you need energy, uh, we basically, it's like, even if you have gold in your hand, you really cannot go to a market and buy something with the gold unless until you convert that to a dollar. So ATP is such a molecule. It's our energy, it's a currency, okay, energy coin. So everything needs to get converted to ATP to be utilized by us, and that is done by these redox reactions. Okay. So mitochondria is basically doing that redox. Now, um, so there are other important redox reactions going on in our body, like oxidation of different substances, toxic substances. We get rid of these toxic substances by oxidizing it. Okay, like methanol. Okay, we oxidize to formaldehyde. Okay, and this formaldehyde gets further oxidized to formic acid, and which eventually get oxidized to carbon dioxide and water. So there are also defense used as like defense mechanism in our body. So that's the importance of this redox reaction. But you will learn more of this in the biology classes. But the chemistry, if you understand the chemistry, you'll appreciate it more, what it is doing. It's an amazing thing, right? Like all these 40 steps that it is going through, breaking down glucose, eventually to get acid gradient and then a phosphate bond. Okay, but in between, all these other things that are produced are also used as building blocks. Okay, like citric acid, malic acid, and things like that, fumarate, citrates. So these are also used as building blocks. Pyruvate, you know, uh, we get acetyl CoA, so for lipid synthesis and so on. But the main, so it's used as a building block as well as for energy. Okay. Now so here we are coming back to our chemical equations again and some mathematical calculations. So, so in the previous section, we did three conversion factors, right? So we use the molar mass as the conversion factor. The first thing is the Avogadros number. So that's the first thing we learned. Okay, the Avogadros number. That's the conversion factor. And we saw the mole as a conversion factor, and we saw the molar mass as a conversion factor. Now, if you look at this relationship here, okay, this equation, what it tells you, if you look at this, but it has to be balanced. Very, very important, okay? Very, very important that whenever you deal with chemical equation, they must be balanced.
Mm.
So do not work with unbalanced equation. So this is a balanced equation. And if I look at this equation, what does it tell me? It tells me that two atoms of silver reacts with one atom of sulfur to give one molecule, okay, or one formula unit, because this is ionic compound. In case of ionic compound, there is not really molecule because ions just come together, okay, by attraction. So we say formula unit. So it gives one formula unit of Ag2S. Now, if you multiply the whole equation by mole, which is Avogadro's number, okay, so I can say that 2 multiplied by, I can actually, multiply it by any amount, okay. So if I multiply by 100, then I'll get 200 silver plus 100 sulfur to give 100 Ag2S. If I multiply by Avogadro's number, then I'll say 2 multiplied by this amount, 6.02 10 to the power 23 silver atom uh, plus 1 multiplied by 6.0 to 10 to the power 23 sulfur atom will give me 1 multiplied by that many atoms. Now, that's kind of, a little bit hard. So we just say mole. So mole is basically this term, this count. So 2 moles of silver plus 1 mole of sulfur to give 1 mole of Ag2S. And now we can convert the mole to grams using molar mass. So I can say 2 multiplied by 107.9 grams of silver plus 1 multiplied by 32.07 grams of sulfur to give 247.9 grams of Ag2S. So you can do all these conversions with one single equations. And importantly, if you add them up, the left-hand side, and you add all the right-hand side, you can see they're equal. So that conforms to the law of conservation of mass. So matter is neither created nor destroyed. It should be equal, okay, in a chemical reaction. So that's the basic actually in chemical, when writing chemical equation. Now, if you look at what we did, so this is the guide to calculating quantities of reactants and products. So you need to have a balanced chemical equation. That's the first thing. And you have to have all the formulas correct. Okay. So, and you have to balance it. So you have to use coefficients to write the chemical equations. So once you have that, then you figure out, state the given and needed quantities. So what is given to me and what is asked? So if you are doing pancakes, okay, and you are given flour, how many cups of flour? And how many pancakes do you need? So, or what do you need? What are you trying to get to with that flour? So same with a chemical reaction. So you are given silver. What do uh, that's the given quantity. Sorry. And you know how much is given. And you want to figure out what is needed. Okay. So that's the first step, identify, okay, what is given and what is needed. And then use coefficients to write the mole factor. So this equation is a mole relationship, and that's called stoichiometry. Okay. So this relationship, this mole relationship, okay, this is called stoichiometry. That's a mouthful, but a term that will come across quite commonly. Stoichiometry. Okay. So determine the stoichiometry. How to determine the stoichiometry? Stoichiometry is two. Here we have a one, and here we have one. This is mole to mole relationship. That's the stoichiometry. Okay. So now everything is there in the equation already. So you have to just use it. Okay. So you just need to go ahead and use it. So set up the problem and just go ahead and use it. So now here we have a simple question. So in the chemical reaction of iron and sulfur, how many moles of sulfur are needed to react with 1.42 moles of iron? So this given quantity. See, here in this table, we have this given quantity. Okay, 1.42 moles of sulfur. And what is asked? How many moles of sulfur is reacting? So moles of sulfur is what I need to find out. That means my moles of iron must cancel out and moles of sulfur remains. So we are going to use the conversion factor. Okay. Now, first you need is the equation. So that's, yeah. So iron plus 3s, and that has to be balanced. So 2 iron plus 3s to give Fe2S3. So what is given to me is the mole of iron. Now, what it tells me that 2 moles of iron reacts with 3 moles of sulfur. So that's the conversion factor. So in step 3, we are writing this conversion factor. Which one should I use? The one that will cancel the mole of iron. So that means I'm going to use the second one, so that the mole of iron cancels out and sulfur remains, and the correct answer is 2.13 mole of sulfur. So basically, the same thing that you did, in a, when you were doing the Avogadros number, the moles and everything. But you know, again, this is these are interesting in the sense that once you get the idea, you use it uh, like uh, the same way for all calculations, just like a recipe. Think of this reaction like a recipe, like a cooking recipe. You have the ingredients, which are iron and sulfur, and the product is iron sulfide. And now you're asking the question that if I have this much iron, how much sulfur do I need? So if I have this much flour, how many eggs do I need to make my pancake? You always do that in the kitchen without even blinking your eyes. But what you are what you are doing at the back of your brain, basically, you are using conversion factor. Now we are just writing it out. That's all. So nothing different from your kitchen recipe. So uh, do not get you know uh, intimidated by this because it's math. You are doing it all the time. So just do it like that. Okay. Just like you do, but you have to write it. You have to write the unit. That's what you are trying to learn. Okay, how to use the units, how to use it as a conversion factor. That is more scientific way. Okay. Now we can join all this together, to go from grams of A to grams of B. So we did from moles of A to moles of B. Now we can connect it, right? So this is our stoichiometry in the middle. Moles of A giving me moles of B. Now I can have these two flanking ends where I have the molar mass. So I can basically go from grams of A all the way to grams of B. Now, why it is important or useful? Because we deal with grams. So if I am told how many grams of A I have to take, I can easily take it rather than somebody asking me, take this many moles. Okay. So this is basically, putting everything together. That's all. Okay. So here we have a question that acetylene, the C2H2, burns in oxygen, okay, and is used for welding metal, oxyacetylene flame. The equation is given to you. Okay, if not, you have to balance it. Okay, make sure that is balanced. Now, this balanced equation, the question is how many grams of carbon dioxide are produced? That means grams of carbon dioxide, the product is produced from 54.6 grams of acetylene. So you always have to go to moles. You have to be able to use the equations. You always have to go to moles. That's very central here. So you go from grams of acetylene to moles of acetylene, from moles of acetylene to moles of carbon dioxide. Now to go from moles to moles, we are going to use the chemical equation. To go from grams of acetylene to moles of acetylene, we're going to use the molar mass of acetylene. Now you can convert the moles of carbon dioxide to grams of carbon dioxide again by using the molar mass of carbon dioxide. Okay. Now, the coefficients, the equations that we have, basically, tells me that this is the stoichiometry, the one in the pink and the blue. Okay. Now here we have the molar mass. 1 mole of acetylene is equal to 26.04. Now follow the units. So even before I start writing number, I write the units. So that is what we taught, right? We learned in the measurement chapter. Follow the units. So grams of acetylene must cancel out. Okay, mole of acetylene means in the next step, mole of acetylene must cancel out, and in the next step, mole of carbon dioxide must cancel out. So your units must be arranged like this. Okay, and then you just write the numbers that you have, associated numbers, and multiply them, and you get 185. So this is three significant figure, and that's why your answer is in three significant figure. 185 grams of carbon dioxide are produced. Now, energy in chemical reactions. So all chemical reactions involves energy. So even when you are burning gasoline, you have to give a spark. Okay. Now, this is a brief of how reaction proceeds. You have a reactant, okay, and is finally giving you a product. Now, if you look at the reaction progress, and if you there's a way of measuring energy of the reaction vessel, you will see that in order to go from uh, reactant to product, it has to go uphill in energy. So it requires energy, and then it comes down. So this activation energy, this is called the activation energy. Now, why is it necessary? So this is the amount of energy, at least. So you can think of it that you want to cross the hill. You can only cross the hill if you can go to the hilltop and then come down. Why is that necessary? That's because chemical reaction. If you think of what a chemical reaction is, it's in order to basically breakage of bond. Okay, initially there must be some bonds must be broken in order to form newer ones. So you cannot just form bonds, because we saw that the number of bonds are kind of limited. If you are looking at carbon, it has 4 bonds. Okay. Now if you're starting with methane, where you already have 4 bonds, some bonds has to be broken, because otherwise carbon is not going to form carbon dioxide. So activation energy is defined as the amount of energy required to break the bond, okay, before it can do newer bonds. So even though the reaction apparently looks favorable, it will not happen unless until you give it some energy, like a spark in a car, okay, to burn the gasoline. So the concept of activation energy is analogous to climbing over a hill. So to reach the destination, you must spend energy to go to the hilltop. Okay. And once you're at the top, you can easily, run down the other side. So now, in order to break the bonds, how does the bonds break? So you can imagine various, uh, uh, not various ways. Basically, there is one way we can think of that the bonds can break. They need to collide. The molecules need to collide, and collide with such a force, such an energy, that it is able to break the bonds. So basically, 3 conditions required for reactions to occur: collision, okay, orientation means proper direction, because the bond has a direction, so it has to be oriented in the proper direction, and enough energy to drive the reaction. When you say enough energy, energy must be enough to break the bond. Otherwise, the reaction is not going to happen. Okay. So these are 3 important parameters that you need to know. And so activation energy is the energy needed to convert the reactant molecules to product. Okay. And how it happens is they collide, and you have to to have enough energy during collision, they need to minimum have this activation energy. Okay, that much energy has to be given to the molecules so that they collide with enough force to break the bonds and then form new bonds. Now, if you look at this reaction here, the 2 situations we discussed here. In the first figure, you can see in the first graph, the reactant is at higher energy than the product. So when the product is formed, the product being at lower energy and the reactant being as high energy, there's an excess of energy that's left over, and that is released. Okay, and so heat is released, and this type of reactions are called exothermic reaction. And when there's exothermic reaction, you write the heat like this as a product, because heat is produced. Okay, so it's written as a product. Now you can have an opposite situation where the reactant is at lower energy and the product is at higher energy, and then you have to give heat Heat is absorbed in order to become the product. Okay, and we are familiar with both these kind of reactions. Like when you're burning gasoline, that's exothermic reaction, or your hot bag, okay, hot pouch. Similarly, you have a cold pouch, okay, like used for pain or something. So you basically break the package inside. So what you are doing, you're trying to do a reaction that will absorb energy. Okay, so when it absorbs energy, it's endothermic, it's become cold. So energy is absorbed, so heat is retained on the left hand side, on the reactant side. Okay, so this is the simple consideration here: exothermic, endothermic. Heat is released, that is on the product side, and heat is absorbed on the reactant side. Now the rate of reaction, the reaction processes at different speed. Okay, that is called the rate. So rate of reaction is measured by the amount of reactant used up or formed in a specified time, per unit time. Okay, that is how Now, how can we increase? How is rate affected? What are the parameters that affect the rate? And one of the parameters is definitely temperature, because we know that as you increase the temperature, there will be more collision and the reaction will get faster. Okay, so greater the number of collisions, okay, more reactions is going to happen. And we say frequency of collision. So there will be more collision, so more reaction. Concentration is another term. So if there are more molecules, they're going to collide more. So if the concentration is more, then the reaction rate is also going to increase, because the collision is going, number of collisions is going to increase. Another important factor is a catalyst. Now, what is the catalyst? So catalyst, they increase the reaction rate. Okay, so they make it faster. So if you add, some additives there, it becomes faster, and they are called catalyst. So you can see some. So how do they make it faster? They basically reduce the activation energy. Now, this is all you need to know about catalyst. So, and one important question with which you big chance that you might get in the exam, that what is the role of catalyst? The role of catalyst is lower the activation energy. So you do not need to spend that much of energy to go uphill. Okay, so you can do it at much lower temperature, much lower energy, and this is a very, very important thing. Okay, so use like palladium, platinum catalyst in inorganic reactions to do hydrogenations. Okay, hydrogens of fat. Okay, or when you see that artificial butter, I can't believe it's not butter kind of stuff. So those are basically made from oil, by hydrogenating oil, and they use the catalyst. Okay, nickel catalyst. Now, so enzyme in our body, enzymes are biological catalyst. So you can see enzymes. So enzymes, if you want to burn glucose in your kitchen, you have to raise the temperature to 200 degrees centigrade, right? And then you can get this caramel, uh, or when you're burning sugar. But our body does that at room temperature, at not room temperature, at our body temperature, which is 37 degrees centigrade. And how? By using enzymes. So enzymes are basically proteins which act as biological catalysts, catalyzing many different reactions in our body. And one of that is glycolysis, the burning of glucose. Okay. But they're the master player, going around doing the job. But they are doing it at much lower temperature by lowering the activity. The enzymes, the structure, at the surface basically binds the molecule and activates it. That's why the shape of the molecule enzyme is so important. And the enzymes are delicate, because if the shape is destroyed, it cannot catalyze anymore. It's like you can say like a jelly. Okay, very delicate. Uh, and we say molten globule, okay, or something like that. So very delicate. So you need to preserve enzyme. That's why if you have a protein, if you have enzyme, we keep it in the refrigerator. Do not freeze thaw too much, because they will fall up. They are so delicate, but their surface gives it a shape so that they're able to activate the desired molecule that they are, activating. Like hexokinase is the enzyme that phosphorylates glucose in our body, the first enzyme in the uh, in the glycolytic pathway, and the enzyme has a pocket where glucose can specifically bind, and then phosphate group is added to it, and it is doing this reaction at a body temperature, 37 degrees centigrade, okay, very easily. But if you just mix glucose and phosphate in the lab, it will not happen. So why is that? Because that enzyme hexokinase lowered the activation energy of the reaction. So that's the general role of the catalyst. They lower the activation energy. So please remember that phrase, okay? It lowers the activation energy. So that's basically our chapter, okay? Now, again, lot of things in this chapter. Uh, so we learned about moles, we learned about molar mass, we learned how to convert from moles to grams and grams to moles. We use the mole-mole factor balancing of equations, mole-mole factor, the stoichiometry, and using molar mass, we could, calculate the quantity of the reactants and products. So that's this is called stoichiometry in general. Now, if you look at chemical reactions that we learned, okay, so these are chemical quantities. We learned about chemical equations, how to write chemical equations, how to balance them using coefficients. We learned the different kinds of chemical, reactions, combination, decomposition, single replacement, double displacement, and combustion. We also learned about oxidation reduction, where there's an actual gain or loss of electron, and they are energy producing, reactions in our body or in nature. Okay. Now, we also learned about exothermic, endothermic reaction. We learned about activation energy here. We learned about reaction rates. And we learned how they are getting affected. There are three things that affect the reaction rates: concentration of reactant, temperature, and catalyst. Okay.